Hello everyone, I hope you're doing well. We are going to find out the linear density for BCC directions, and these are the three directions that we are going to consider. We'll find out the linear density for these directions by considering a body-centered cubic crystal system. Okay, first of all, we need to find out that what is the formula that we will follow. And the formula that we will follow for any kind of crystal, if you want to find the linear density, this is the general formula, and it is like net number of atoms lying on the line, that was a lengthy line, divided by the length of the line, and all these parameters are considered, or we find them out within a single unit cell. Okay, only one unit cell is considered, and net number of atoms that lie on the line considered within one unit cell, and the length of the line within one unit cell. Okay, you do not need to mention that it is within one unit cell. You just need to store that information in your subconscious mind. You just don't need to mention it right there, but it is an important thing to remember. Okay, so first of all, we'll find it out for 100 direction. Okay, now the first step is to draw the direction. Okay, before drawing the direction, you just need to draw the unit cell you are considering, and the unit cell we all know is a cubic unit cell, and here it is the cube. All right, this is y direction, this is x direction, and this is the z direction. And since all Miller indices are positive, that is why I'm considering this point as the origin. Okay, this point is taken as origin for all positive Miller indices. Okay, if the Miller indices are negative or something like that, you just need to shift the position of the unit cell depending upon which coordinate is negative. If you are confused how to draw the directions from given Miller indices, then the video's link will be in description box. And additionally, if you want this video in Urdu or Hindi as language of instruction, then the video link will be in description box. I'm doing it in English language again. The similar video is already there on the channel, but I'm doing it again for those students who couldn't understand Urdu or Hindi. Let's begin. The first step is to draw the direction, and in drawing the direction, you have to divide the LCM of the non-zero Miller indices with the denominator. This is one of the basic steps that needs to be done. In case of these directions, it doesn't need to be done because the LCM is 1. Okay, so dividing by 1 doesn't brings any change, but for other directions like 2, 1, 0, like these, you have to divide the LCM of non-zero Miller indices. Like in case of 2, 1, 0, 2 and 1 are non-zero Miller indices, we'll find out its LCM, and in finding out the LCM, it is like 2 LCM is there. You will divide 2 with all these digits. Okay, and you get 1, 1 by 2, and 0. These are the coordinates that you will follow in order to draw the direction. Okay, but in case of 100, the non-zero digit is 1, and if you take the LCM of 1, the 1 is the result, and if you divide 1 by these digits, you again get what it was before. Okay, this is the first basic step. I was just mentioning it just for you to remember the procedure, because normally the students who are finding the linear density for linear density questions, they were also required in some other ways to draw some directions from Miller indices. That is why I was just making you practice the procedure again and again. And these are the coordinates now. The first one is for x, the second one is for y, and the third one is z. Okay, first one is x coordinate, second one is y coordinate, and third one is z coordinate after performing that division process. Okay, so from origin we'll move 1 unit along x-axis. Okay, we'll move 1 unit along x-axis. Okay, 1 unit means from one edge to the other edge, okay, of the unit cell. This means 1 unit. Okay, and after that we'll move 0 units along y-axis and 0 units along z-axis. From this we need to go nowhere because y and z coordinates are 0. So this is the final destination, this is the initial end from this to this. Okay, this is the direction, this is the line under study, and we know that this is a BCC crystal system. Okay, body centered cubic crystal system. So the atom that are possibly there are this one atom, corner atom, and this corner atom. Okay, none of the other atom will be lying on this line, we already know, because the body center atom will be there. Okay, the corner atoms will be there. So these are the extra details that will just add to the confusion, and they do not need to be drawn. Okay, you just need to draw the atoms that are possibly lying on the line. Okay, so these are the two atoms. Okay, and the center point of the atom is lying on the edge of the corner of the unit cell. Okay, this is the center point of the atom is considered as spherical in shape, and its center is centered on this point, these lattice points, which are the corners of the unit cell. Okay, from the center of the atom to the edge of the atom is the distance, which we call as radius. Okay, which is half the diameter. So how we are going to find out the net number of atom lying on the line? For this, we have to consider which fraction of the diameter is lying on the line. Okay, we can see here that only half the diameter of the atom is lying on the line, the other half is not being intersected by this line. Okay, we are considering it within one unit cell, and only half the diameter is within the line. So we'll consider its contribution to the atom as 1 by 2. Okay, if the line is intersecting the whole atom's diameter, if the whole atom's diameter is lying on the line, then its contribution is taken to be 1. But if it is from center to the edge point, if the atom's half diameter is within the line, then we consider its contribution to the line as 1 by 2. Okay, so it depends upon how which fraction of the diameter is lying on the line. Okay, half by this atom, and again half by this atom also, because from center to the edge point of the atom it is half the diameter, and half the diameter is only within that line. So half by this atom and half by this atom, so capital N will be 1 by 2 of this atom and 1 by 2 of this atom. We'll add them up and we get 1. Net one atom is lying on this line. Okay, and the length of the line, we know that it is a cube, and cube has similar dimension in every axis direction, from one corner to another corner. So this length is, let's say lattice parameter is a. Okay, and it is equal in all direction for cubic unit cell. So BCC is also a cubic unit cell. So this is a in this direction, a in this direction, a in this direction, a in this direction. Parallel to the axis directions it will be a. For all other different directions it will not be. Like this direction is not a parallel to x, y, or z axis. Okay, it is a different direction, but this direction is parallel to y axis, that is why it is a. This direction is parallel to z axis, that is why it is a. This direction is parallel to x axis, that is why it is a. So from one edge to another edge parallel to the axis lines, the length will be a. Okay, this length is a also. So the length of the line is a. All right, now we need to put the value of these n and l into this formula to get the linear density for 1 0 0 direction. Okay, capital N came out to be 1 divided by a. Okay, so 1 over a is the linear density in 1 0 0 direction for BCC crystal system. Now sometimes you are required to express the linear density in terms of lattice parameter only, so this is it. But sometimes it is required to express it in terms of the atomic radius of the atom forming up the unit cell. Okay, these are the atoms and they have particular radius that I was talking about, which is, let's say, capital R. And sometimes you are required to express the linear density in terms of the capital R radius. So there is a fixed relationship between lattice parameter and radius capital R for BCC crystal system, which is 4 by under root 3 capital R. Whereas the lattice parameter in capital R is the atomic radius. We'll derive it. I'll drive it. I will put that patch of the video next on. But I'm just plugging that value into this expression to get the linear density of 1 0 0 direction in terms of the lattice, in terms of the atomic radius. We'll just simply plug this value of a right there. Okay, this is true only for the BCC lattice. For FCC lattice it is 2 under root 2 capital R. Okay, for FCC lattice this relation is between a and capital R, but for BCC lattice this is the relation. Okay, we'll simply put the value of a right there, and what we get is okay, and R is in the numerator, sorry. So under root 3 comes above, and this is the linear density 1 0 in 1 0 0 direction in terms of the atomic radius. Okay, So these are the numerical values expressions. Sometimes you are given the value of lattice parameter or even the radius of the atom. The atomic radius is, let's say, given for cesium atom to be 1.9 angstrom. Okay, you just need to put the value 1.9 angstrom is 10 is per minus 10 meter. You will plug that value into this expression. You will solve it using your calculator. The resultant value, you write it right there, and the units will be atoms per meter. Okay, since it is a linear density, linear, that is why per meter. Okay, atoms per meter will be the units that you will mention alongside the numerical value. Okay, that will come out as a result of your calculation. If the lattice parameter is given, then just put the just use this one relation. If lattice parameter is given, to find the numerical value of linear density, and if atomic radius is given, then use this relation. Use the relation accordingly depending upon which parameter is given. Okay, so we have successfully found the linear density for 100 direction. And next, in the coming section, I will link the patch of the video that will explain how this relation will come out, and you can skip it if you don't want to watch it. It is optional, you know. You can just remember that relation. Sometimes it is given as a question to prove that this relation is true for BCC lattice, so you can do it for that one purpose also. But if you want to skip it, you can skip it. And after this derivation, I will derive linear density for 110 direction and then for 111 direction. Okay, linear density for FCC directions are also done, and the link will be in then description. You can follow the following procedure. For BCC crystal system, we can find out the particular relationship between atomic radius and the lattice parameter A, and it is like these atoms in the diagonal are completely attached. Okay, and if you draw a vector from this to this, okay, and this and like that, this whole triangle is a right angle triangle with right angle right there. Okay, this is not necessary that you derive it every time you are finding out the linear density. You can also remember the relationship between A and R, which is lattice parameter and atomic radius for BCC. Okay, you can directly remember it or derive it, it's your choice. So we can derive it as follows. This length is A. Okay, this is the length of the line, this line which is parallel to the z-axis, so, and it is completely within the unit cell, so that length will be A, and this length could be found out using this right angle triangle, and this is the length A and this is length A also. Okay, and this is a diagonal length and it is not parallel to either x or y axis, that is why it is not A, it will be different. And since it is a diagonal and is making up it is acting as a hypotenuse between this base and perpendicular, we can use a Pythagoras theorem to find out its length, and after finding out its length we'll use Pythagoras theorem again to find out the relationship between A and R for BCC system. Okay, so let us find this length first. This is A, and this is hypotenuse. Let's say it is H. So base square, which is A, plus perpendicular square, which is A again, that is equals to hypotenuse square. So this is 2A square equals to H square, and if we take under root on both sides, we'll get H equals under root 2A as the length of this hypotenuse. Now this length is under root 2A, this is A, and this length can be found out in terms of the atomic radius, as we can see here that the half of the atom is lying on that line, which means one radius is there. This length is one radius, and this length is the whole diameter of the atom, which is 2r, and this length is again half the diameter, which is r. So if we add up these chunks of the length, then we'll get the total length of this diagonal line, which will be r plus 2r plus r, which is 4r. So now this is another right angle triangle with hypotenuse 4r, base under root 2a and perpendicular A. We'll use the Pythagoras theorem again with 4r as the hypotenuse square, that is equals to base square, which is under root 2a square, plus perpendicular square, which is A again. It will become 16r square equals 2a square plus a square. 3a square equals 16r square, and we will find out the value for A, which will become 16 by 3r square equals a square. Taking under root on both sides, we will get 4 by under root 3r equals to A. Okay, this is the relationship between the lattice parameter and the atomic radius for BCC system, and it is true for all. It will be used for all directions. Okay, it is a general term for BCC crystal system, and it will be taken as a true relation for if you are considering the PCC system. Okay, it will be different for FCC. For FCC, it is A equals 2 under root 2r. For FCC, this is the relationship between lattice parameter and the atomic radius, while for BCC, it is this. So now we are going to find the linear density for 110 direction, and first of all, we'll draw the cube, and this is the cube, and let's say the lattice parameter is A. In cube, the lattice parameters are equal. A equals B equals C. The three lengths are equals to each other. So let's say each length is A. So this is the origin, this is y direction, this is x direction, this is z direction, and these are the edges of the unit cell. Okay, these are the corners of the unit cell. Now 110 direction could be drawn as follows. This is the coordinate for x direction, the second one is for y direction, and the third one is for z direction. So we have to move 1 unit across x-axis. 1 unit means from origin to the corner of the unit cell. So from origin, we'll move 1 unit along the x-axis to the corner of the unit cell. And since y is also 1, the coordinate for y is also 1. So from this point onwards, we'll move 1 unit along y-axis, and this is the y direction. So we'll move in this direction in 1 unit, so it means the other corner of the unit cell. Okay, we have moved 1 unit along x-axis and 1 unit along y-axis. And since z coordinate is 0, then it means we do not have to move along z-axis. So this is the final destination, and this is the initial. So from initial to final, we'll draw a vector, a straight vector. That will be the direction 110. Okay, this is the direction 110. Okay, and we need to find out its linear density. So the formula for linear density, as we know, is for 110 equals a number of atoms lying on the line divided by the length of the line. Let's say the length is capital L. We'll find out what length it is. So this length is from one corner to another corner in the x direction is A. This length is A also. This length is A also. All these lines which are parallel to the axis lines are A in length from one edge to another edge. Okay, like this length, this one is parallel to the y-axis, so this one length will be A also. But this one length is not parallel to x, y, or z axis. That is why this length will not be A. So this is the formula, and we are considering BCC, body centered cubic crystal system. So for this, we know that the atom that lie on this line would be the first, that is the corner atoms. Okay, and all other atoms will lie outside that line. None of the other atom will lie on this line particularly, because other atoms will lie right there. The body center one will be there, and the others will be there. So only these two atoms, some part of these atoms will lie on this line. We'll find out what part they contribute to the line, but only these two atoms are under consideration, and none of the other atom will be there. So we can see here that only half the diameter of the atom of this atom is lying on this line. Okay, so the center to the edge, which is the radius, and radius is half the diameter, so only half contribution of this atom is to the line. And similar cases with this atom, only half the diameter is lying on this line. We only see if the full diameter of the atom is being intersected by the line, then we consider its contribution to the line as 1. And if half of the diameter is within the line, then we consider its contribution as half, as I told earlier. So half by this atom and half by this atom. So the n in this case will be half by this atom and half by this atom, and it will be 1. Okay, secondly, we need to find out the length of the line. This line, the length of this line, and this line, since it is not parallel to y-axis or x-axis or z-axis, so this length will not be A. Okay, these lengths are A, and this length needs to be determined. We have already found this length from the previous derivation when we were finding the relationship between A and R, capital R, but we can see it again as this length is A, this length is A, and this is hypotenuse of this right angle triangle with right angle right there. Okay, between x and y direction there is a right angle. That is why we are considering right angle right here. This is base, this is perpendicular, and this is hypotenuse. So using the Pythagoras theorem, we can find the C, which is the length of the line. So it could be found as follows. Let's say this is L. Okay, because we have denoted L right there as the length of this line. So L square, that will be equals to A square plus A square, base square, which is A, and perpendicular square, which is A again. So A square plus A square, which is 2A square, L square equals 2a square. Taking under root on both sides will give us under root 2a. So the length of the line, 110 direction line within a single unit cell is under root 2a. So putting these values, we will get the linear density in terms of the lattice parameter. So 1 is the n's value and L is under root 2a. So 1 over under root 2a is the linear density for BCC crystal system in 110 direction. Okay, and this is the value of linear density in terms of lattice parameter, and we know that the relationship between A and R for BCC is A equals 4 by under root 3 capital R, as we have previously found. I have already derived it, you can see here. Okay, so this is the relationship between them. So we can also express the linear density in terms of the atomic radius of the atom making up the unit cell or crystal, and putting the value of A right there in denominator and solving it, we will get this will jump above and 4 under root 2 capital R, or we can write it as like, no, it's okay. So this is the final result for linear density for BCC crystal system in 110 direction. Okay, next we are going to find out the linear density for 111 direction, and sometimes you are given the value for lattice parameter or the atomic radius for the atom, like cesium atom, sodium atom. So you just need to put the value of AR capital R, whichever is given to these formulas depending upon which value is given. And these are normally given in angstrom units, so 4.8 angstrom, for example. So you need to put the value 10 to the minus 10 meter. 1 angstrom is 10 to the minus 10 meter. So angstrom is equals to 10 to the power minus 10 meter. Along with angstrom, you do not mention meter, because angstrom itself is equals to 10 to the power minus 10 meter. Okay, so you do not need to write meter when the angstrom is there. So you will put the value of A right there, and after calculating it from calculator, you will write the result as the numerical value with units of atoms per meter. Okay, these are the units for linear density. So now we need to calculate the linear density for 111 direction. So here is another cube. Okay, another cubic unit cell, and this is y, this is z direction, this is x direction, and this is y direction, and this is the origin. Since the Miller indices are positive, so the preferred origin for me is this one point. So from origin, we'll move 1 unit along x-axis, then y unit along y-axis, and then 1 unit along y-axis, and then 1 unit along z-axis. So from origin, we'll move 1 unit along x-axis, okay, to the other corner, 1 unit along y-axis from this to 1 unit along y-axis, this is the y direction, and 1 unit along z-axis, and this is that vertical distance. So this is the final destination, this is the initial point. From initial to final, we will draw a straight vector, which will be the line of interest for us. Okay, this is the 111 direction. Okay, and for BCC crystal system, we know that where the atoms lies when the vector is like a diagonal from one edge to another, there is a one atom right there, the other atom right there, the complete centered atom, body centered atom. This one atom will also lie on this line, and the last atom is this one. All other atom will lie outside this line. Okay, all other will lie outside of this line. That is why I'm not drawing them to avoid any kind of confusion, because they are not needed. So these are the 3 atoms that are there, and their some part is contributing to this line. Let us see what it is, and the formula for linear density, we'll mention it first, is equals to n divided by capital L. Okay, so we can see here that only half the diameter of this atom is lying on this line, on not the complete but the half the diameter. So half contribution will be considered by this atom to this line. Okay, but this body centered atom is completely intersected by this line. The whole diameter of this atom is intersected by this 111 line. That is why one whole contribution will be considered by this body centered atom, because the whole diameter is lying on the this line. Okay, and again the half diameter is intersected by this line. That is why we are taking 1/2 as this atom's contribution to the line. The other half is not within the vector line within one unit cell. Okay, so half by this atom, 1 by this atom, and half by this atom. So the total atoms that are lying on this line are the sum of all these values, and we will get 1 plus 1, which is 2. Okay, net 2 atoms are net number of atoms that lie on this line are 2 within one unit cell. Now we need to find out the length of this vector, and we have already found its value in terms of radius, but we'll do it again. We'll first need to form a right angle triangle, which will be right like that. Okay, this is a right angle triangle which involves this vector also. Okay, so this length is parallel to z axis, so this length is a. This length, as already found, is under 2a, and this length needs to be calculated, which is, let's say, capital L. So you will use Pythagoras theorem to find out its value, and this is hypotenuse, so its square equals a square perpendicular square plus base square, which is under root 2a. Okay, so a square plus 2a square, which is 3a square. So L square equals to 3a square, and L will be equals to, taking under root on both sides, under root 3a. Okay, so this is the length of this line, so we'll put the value of capital N and L right there, which is 2 divided by under root 3a. Okay, this is the linear density for BCC crystal system in 111 direction. Okay, in terms of lattice parameter, and after putting the value under root 3 by 4 r, no, it's 4 by under root 3 capital R. Okay, a equals 4 by under root 3 capital R. So putting the value, a is equals to 4 by under root 3 capital R. So under root 3 cancel out. 2 ones are 2, and 2 2s are 4. This one cancels out 2. So we are left with 1 over 2 capital R as the linear density. So this is the linear density in terms of the atomic radius, and this is the linear density in terms of lattice parameter in 111 direction. Okay, so we have successfully found the linear densities in 3 directions for BCC crystal system. In next video we'll see for FCC, and we'll also see how to find the planar density for BCC and FCC crystal systems. The Urdu and Hindi versions of the similar video are also there. You can find the link to these videos in description box, and do like, share, subscribe. Goodbye.